Okay, thank you very much. So now we're going to continue with this plenary talk with Henrik Jensen from Imperial College, UK.
Thank you.
Welcome, Henrik.
Yeah, and thank you very much for giving me the opportunity to be back here. It's my first time to this specific institute, but I've been many times to Mexico. I'm very impressed by the institute. It's a lovely place. I'm going to talk about complexity science. My title, as you can see, is about emergence and how to quantify it. But I'll start out with some deliberations on what complexity science is about. And then I'll discuss emergence, what we mean by that, or what I mean by that, commonalities across different systems, and how to identify emergent structures using, well, physics as an example where there's a formalism, and then talking about information theory as a tool when there isn't a theory of the underlying mechanisms in the system you're looking at. Okay, but I think it's important to think a little bit about what complexity science is about. And the reason I think this is that we in the United Kingdom experienced some 10, 15 years ago that the funding agency decided that there is no such thing as complexity science, and therefore they stopped funding complexity science. And this was after having developed a number of doctoral training centers in complexity science. Then the EPSRC, as they're called, decided that, okay, this is not really a real proper science. So they wanted rather to fund individual cross-transdisciplinary projects. And I think that's a bad decision for UK and maybe for everyone that involved in complexity science. So I thought a little bit about how to define what complexity science as a science in itself could be. What is its subject matter, in the sense that say, if you asked what is mathematics about, then mathematicians at least would say it's about study of patterns, or physics is the study of innate matter, biology about matter that's alive, if you like. So what is it that complexity science is about? And I think one aspect, at least, that's very important, the study in a systematic way of emergent structure amongst interacting components. And I'll also argue that as ever when you do theoretical studies, there can be a virtue in trying to be simple. So I thought it would be fun to have some ways to measure, if you like, or characterize the usefulness of theoretical models or approaches. And I thought of two people that have thought about this. O'Keeffe, if you probably know, right, from New Mexico, the American painter, who said this: nothing is less real than realism. Details are confusing. It is only by selection, by elimination, by emphasis that we get at the real meaning of things. So this is a flower. And of course, we all know that Einstein has said all sorts of things. Many of them he probably never said, but it doesn't really matter. I do think he said this: make everything as simple as possible, but not simpler, right? And maybe this is the more important. That one we all use very often, I think. This one is very important to keep in mind, that a theory is more impressive if it's not an ad hoc theory. Of course, we often have a set of data points and we like to try to comprehend what it might be about. And therefore, we start out constructing a theory specifically for that situation. But of course, it's also the overall game or aim eventually to have theories that can cover many different situations. So these thoughts led me to suggest that we can think of a set of propositions for what would make a good complexity theory. So something that's simple, but not too simple, and something that's able to address more than just one specific aspects. And our aim, that's what I think of as complexity theory as itself, its aim is emergence at the collective level. And of course, this is not something new to think about what that is. And I just want briefly to mention that some of the previous complexity scientists that are probably well known to you, Leo Tolstoy, who thought about in his War and Peace, I don't know if you read it, but the remarkable thing of War and Peace is that it's a mixture of a novel and philosophical deliberations on what the nature of history is. And here, what he talks about is, what is it that's the driving force of history? Of course, often we are told that it's the important people, the kings and the generals and so on, but Tolstoy didn't buy that one. He attempts to identify the forces that produce the movement, and he says down here, I think, that it's like, so the effects that actually move history around is like the addition of infinitesimal small quantities, like we are used to in mathematics, right, in integration theory, in the theory of integration or calculus. I think that's pretty nice because it's exactly the opposite of this idea that it's you need to describe what that king has done or what that general has done. It's an appreciation, acknowledgement that the outcome of history is an effect of many different quantities collaborating or interacting. But of course, Tolstoy didn't try to identify what these emergent structures might be that moves history around, but Karl Marx did. And I think he's probably the first in social science that actually tried to identify the building blocks. And I'd say this is one of the aims, at least, of complexity theory, to try to identify the building blocks of a system of many interacting quantities. And he did it, as you all know, of course, suggested that it was the classes, right? And this is since Marx, I guess it hasn't been developed very much, this approach to try to identify the structures in society that's actually dynamical blocks that move. New Labour in UK tried to come up with something new, obviously, and discuss stakeholders, but it has the drawback compared to Karl Marx that he could actually define the classes, as I'm sure we all know, in terms of how you relate it to ownership of the means of production. Stakeholders is sort of everything. Everyone who has an interest in something. It's stakeholders in the school are the kids and the parents and the teachers and the government, so on. So I think that this is in social sciences, it's definitely still important to try to do this trick. It's not easy. I don't think that Karl Marx was the final word, obviously, but I do think that it's worth continuing. And I remind you how successful agent-based modeling can be to analyze at least quantitative questions. So I think you may all know about the Schelling model, and I just want to mention it again because it is a good example of how a very simplified model can address a very complicated question. So Schelling developed this model in around 1970 as an attempt to try to understand why some American cities were highly segregated in white and black parts. And the conundrum or the puzzle he had was that when he talked to individual people, they were not particularly racist. They're not very afraid of the other type. So how could that be that nevertheless the cities disintegrated into groups of opposite types? And he came up with this simple model where the agents have only one purpose or only one ability, namely to decide if they want to stay in the local vicinity where they are or to move, and the decision is made by how how comfortable they are, and the comfort they feel is determined by what is called the tolerance level. That is, the tolerance level is how big a fraction they want of their own type to be in the neighborhood in order to feel happy. If that fraction becomes too small, then they move. So what would you now, if you haven't done complexity theory, haven't thought about emergent structures and so on, what would you expect would happen here? I think you would expect that you'll see cities with an inhomogeneous population, right? That there'll be a mix of black and white everywhere, but it would not, the difference between the black and the white wouldn't be very great, because it would be limited by this threshold. Because if one type became too small a minority, then they would move. But there's no reason to think that you wouldn't have some heterogeneous mix across the city. But you don't see that. In Schelling's model, what you saw was that the two types segregate into two different regions entirely. The segregation depends on the level of of tolerance. But if the agents have a tolerance level that is less than a third, meaning that they decide to leave if their type constitute less than a third of the population locally, then immediately you have the full segregation. Are these magnets? No, but they could be. So that's a good point, which is one of the reasons I wanted to mention the Schelling model, namely that they could be magnets, they could be atoms on surfaces and so on. So the first thing you may want to say is that they could certainly not be people, right? Because people can't just be modeled by this kind of very simple agent. And of course, that's totally true in one sense. So what does the model do? Why is it important as a complexity science model? I find it's one of the ways to argue why it's important to look at emergence as a subject matter itself, because you have shown here that the collective level can be behaving completely different from what you expect by analyzing the individuals. That's what I said, that from analyzing the individuals in some sort of mean field expectation, you would not have segregation. So if one wants to convince a politician that it's worth investing a little bit in research in complex systems, then this model might be one to use. Okay. Now, the other thing that physicists like to call universality is when you have systems that are completely different, like transition from liquid to solid or from magnetized to non-magnetized, so the systems are very different, but the phenomena can be described by the same kind of concepts. That gives a certain commonality across systems. That's another important point to be aware of, that complex systems actually have this ability, or has this property, that despite of complex systems being very complex, despite the phenomena of segregation in cities being a very, very complex phenomena, it might be that there are certain few ingredients that actually cause the trouble. That's what Schelling's point was, right? And then it turns out that because it's well, in his case, it was just a single parameter, that this kind of phenomena is described by the same mathematical modeling, at least, as segregation of atoms on a surface, for instance. Here is, and oops, here's not what I had hoped. Could we go back to full screen? Very good, thank you. This example I find is really exciting. You see here the behavior of three different systems. This is rain, this is the brain, and this is the very simple-minded model of forest fires. And what you see is the order parameter, the control parameter, which for rain is the humidity. In this case here, it's a measurement from fMRI scans. So in the activity is taken to be the number of signals in the scanner that has a bold signal above a certain level. And in the forest fire, it's the density of trees. I don't know to say much about it, but my point is that these are completely different systems. They do behave under their own dynamics in the following way. There is a curve here, the residence curve, that tells you about how often the system by itself moves into a region where it has this value of the control parameter. And what you see is that it is the same sort of, at least qualitatively, the same sort of behavior you have in rain, brain, and forest fires, that the system spent most of its time in a region where what is called the order parameter picks up. The order parameter is, in the case of the precipitation, is simply how much precipitation comes down. So no rain here, lots of rain here. In the case of the brain, what they took as the order parameter is the size of the largest connected cluster of voxels in the brain that has a certain activity, an activity over a threshold. And in the forest fire, it's the size of the connected trees. So I think this is good news. It means that if you can understand the dynamics of these, of say the forest fire, that's the easiest because that's just a computer simulation, then you might learn something about the dynamical behavior of other very complex systems. Now, some thoughts about how to identify emergent structures. And let's talk about physics and biology first. So the point is that sometimes it's very easy to identify an emergent structure, right? Here we have tornado. It's easy to see it. How would you go about describing that? Well, because it's easy, the length scales are such that we can easily identify it by our eyes, right? Just by vision. Of course, there isn't really any issue. And you would maybe say that if you're in the situation where you want to study the interaction between two tornadoes, if you're so unlucky to be near a situation like this, well, what would you do? You would probably do something like replacing all the complicated flow of the tornado here and the complicated flow of that one by some sort of interaction between the center of masses. Okay, and then see how much you can get out of this. Now, I don't think that tornadoes are often very many together, but there is a system which Gustavo talked about, the 2D XY model, which has become very famous because it's an example of a peculiar because we didn't know that type of phase transition. And he got the Nobel Prize very recently for the identification of what is called topological excitations that drives the order parameter. The model is simple. It consists of these arrows sitting on lattice points, and the arrows have an energy interaction, or an interaction that gives rise to an energy that's lowest if they are parallel and highest if they're anti-parallel. That's it. So that's a very simple model. You can think of a small compass needle sitting near each other. What happens then is that as you increase the amount of energy in the system, so the temperature, is that you form these structures. And you admit, I think, that it's not completely different from a tornado. It's just a two-dimensional one seen from above. And here's another one. And here the flow is the opposite direction. My point is that it sounds maybe rather pedantic, theoretical, boring, I don't know what, but it is an example where the realization of these macroscopic excitations, collective macroscopic excitations, has led to understanding of many properties of a range of physical systems. So the point is that these structures that we call vortices, they cost, of course, some energy, right? Because the lowest energy is when all the arrows are parallel, and they're not parallel here because they have to circle it around. So now the nice thing in physics is that you know what to do if you have the energy of the system, because everything is essentially controlled by energy. Either you use Hamilton equations and you get the equations of motion, or you do statistical mechanics and you do Boltzmann weights. But you have a formalism, an existing formalism that allows you to go from configurations to probabilities. This, of course, we don't have for the brain yet. But let's see how it works when you have that kind of formalism. What Kostelis and Fowlis discovered in the early 70s was that these structures, these vortices, can give rise to a phase transition. And it was particularly interesting because there are fundamental theorems that says there can't be any phase transition in this system. This, I think, is also an interesting story. So Mermick-Wagner theorem says that when you have a continuous symmetry of a system, or in a system, you can't have a phase transition. Now, and that's of course true. If it's a fundamental theorem, it must be true. The point that what was not true was that there's only one type of phase transitions you can't have, and that was the one that leads to an overall magnetization, meaning that these compass needles decide, or whatever you like to call it, are favored to point in one direction. That kind of phase transition can not exist. What can exist is that these vortices can destroy the stability of the system, and by that is meant that if you want to try to make a gradient of tilt of the compass needles, the rotors, you have to, it costs a certain energy. And this is what I try to indicate here. That's called the helicity modulus. But that energy cost suddenly drops to zero at a certain temperature. And it drops to zero because these topological excitations can start to move around. So how does that relate to general complex systems? Well, it's an example where by identifying the collective excitations, the collective structures, you suddenly understand the dynamics of the system. And given where we are, I'll run and show you what comes out of this. It turns out that the 2D XY model is relevant to many different systems, and one of them is a superconductor. And superconductors has the ability, of course, to let current flow through without any energy dissipation. That's why they're called superconducting. And this is true. Let's see, we need this drawing here. This is true as long as these vortices don't move. If they somehow are tied together by an elastic band or something, they do attract each other, because you can see that if they could come close, the closer they come, the less they disturb the vortex field, and therefore there is an attractive interaction. Okay, now if there is no interaction, they'll start to move when you put a current through, and that's because they carry a magnetic moment, and you know there is an interaction between an electric current and a magnetic field. So therefore they'll feel a force that's called the Lorentz force, and since they have opposite sign, the Lorentz force acts in this direction for one of them, and for the anti-vortex in the opposite direction. That's all fine if there is enough interaction between these two to maintain the stability. So make sure that they don't break away from each other. Now, this is all good, and maybe a little bit trivial now that we have realized that they're vortices. But of course, before you realize that you need to look at these systems these systems of multiple compass needles or rotors through the optics of the excited quantities, namely the vortices. Before that, it was not so easy to understand how dissipation, how a voltage comes about. The interaction between the vortices depends on the dimensionality. So if you have just a single layer, the interaction is logarithmic, and as soon as you put a force on, the energy it'll be possible for the Lorentz force to overcome the logarithmic force, because this is linear in separation and the binding force is logarithmic. So you'll always have, as soon as you put a current on, that these vortices will start to move. If you have a layer of superconducting sheets, as you have in high TC superconductors, then there is an additional contribution to the interaction between the vortices that comes from the adjacent layers. And that turns the logarithmic interaction into a linear interaction. And now something interesting happens, namely that now the Lorentz force has to overcome the linear restoring force from the interaction between the layers. This translates into saying that if your current is small enough, it can flow through the superconductor without dissipation, but suddenly, if it becomes larger than a certain threshold, then you start to dissipate. So here we are. You can actually see that in experiments. This is what these curves shows, that the voltage drops to 0 if the current is, if the temperature is small enough so that the Lorentz force can't break the restoring force. So I thought of this as an interesting example, perhaps to at least be aware of, that in physics, you have situations where the identification of the collective excitations, the emergent excitations, allow you to understand something that I don't think anybody would have a way to understand, namely this change in the voltage current characteristics, without having first realized that there are these collective excitations. You could, Karl Marx would say that you can't understand at all the history of society if you don't understand the different classes and the different interests in the political structure. So that's the equivalent. Okay, now, of course, in many situations, we don't have a theory, a fundamental theory that allows us to theoretically first extract the emergent structures. So we'll have to do that by using some analysis of data, of course. And information theory, as I'm sure you all agree on, is certainly one possibility. So what we want to do is, from the multivariate distribution of some phenomena like the brain, that gives you this kind of high dimensional probability function. We want to see if we, from that knowledge of that probability distribution, can understand the emergent properties, the structures of the emergent properties. And then you use the kind of language as redundant interdependencies, synergetic interdependencies, causal decoupling, agency, and so on. So I'm sure you might have, some of you are maybe even like experts on this. So from information theory, you try to extract the properties of the emergent structures without actually knowing what the emergent structures are. And, well, we know from Raphael's talk now what entropy is, so I don't need to tell you anything about it. You know what it is, Shannon's. Entropy is what is basis for information theory at the moment. And then the workhorse is conditioning or mutual information. So I'll show an example where we try to address the question now in evolutionary dynamics, so biological evolution. At what level does selection act? This is a question that has been around since Charles Darwin. Does it act at the individual reproducing organism, or is there something like group selection? This is very difficult to settle from observation, right? Because it's difficult to get enough data over long periods to actually address the question. So we rely on a model we call the tangled nature model, and that consists of individuals that undergo what is called frequency-dependent reproduction. It means the ability to reproduce depends on who else is around. Then they can mutate as they reproduce, or they can die. That's the model. And the frequency-dependent interaction is illustrated here. It means that a monkey, say, or one organism, it doesn't have any inherent fitness. Its fitness depends on who it's around together with, who it's co-evolving with. So that's the point here is that this is a very sad monkey. And the reason it's sad is that there are very few bananas and a lot of lions around. Whereas the exact same monkey is now here. You might not recognize it because it's so happy now. And that's because there's so many bananas, a very few lions. So this is the driving mechanism in the model. And of course, you can formalize that a little bit. And what comes out of it is, first of all, now I'm talking about the population level evolution. You get punctuated equilibrium immediately. And this you see from these graphs. What's shown here is time out there, and then up along the, or rather down along the y-axis, we put a label for the different types. So there is a maximum here of 1,000 different types. And what you see is that the higher a type is occupied, the larger the occupation of that type is, the more yellow. And then it's red, and then it becomes dark. So you see the punctuated equilibrium immediately in that the model evolves and find these configurations of some occupied types that fits together in terms of their interaction and therefore can sustain the population under the action of death, right? Because there's always this probability that they die. And therefore they need to keep up their reproduction so that it can fight against the death. And then you see that these become unstable due to mutations, and they look around in type space and they find a new metastable configuration. Now the question is, as I said, can we from this get some information about whether, in what sense selection acts on the individuals, or is it a more collective thing? And what we do is that we lump the individual types, not the individuals, but the different types. So these suggest different types that have various occupation. We lump them together in groups of size K. We do all the different partitionings we can figure out to do. And then we look at how the, what is called the individuality, and that's simply the information, well, information theoretic mutual information between that group of types at time t and the same group at time t plus 1 divided by k in order to get some sort of normalization. So if it was that selection only occurred at the level of individuals, you would think that this measure is largest for k equal to 1. If it were that the entire population is always selected for, then it should be largest when k includes all the extent, all the existing types. What we find is that there is this peak in between. So what I show here is the size, the k, the size of the groups, and up here, this individuality score. And you see it nicely peaks for mutation rates that's below the error threshold, but you don't want to go into this. The point is that if the system doesn't have wild high level of mutation so that it actually can adopt, then the largest individuality is for bags of types that has a number bigger than 1. So it's not, the individuality score is not largest for the individual type, but it's a collective entity. Okay, this was just one example of how you might be able to identify some sort of collective structures directly from data. Right here, the data are the occupancy coming out of computer simulation, but of course you could probably, if you're lucky to have enough data, do something similar in real systems. Now I'll talk about using information theory to characterize the relationships between different components. Okay. And again, the idea is that you have a multivariate data set and you try to figure out how these different components of the data set related, either synergetically or redundancy. And you can illustrate just qualitatively what we mean by synergy, thinking in terms of the Moromon rings, which I noticed that are very familiar to the center. The idea is that no two of these rings actually intersect, but they lock together in a robust structure as long as they're all three together. Right, so that's synergy, that you need more than just pairs of the components. Here's the exact opposite. You can say, if you know one of these gymnasts, you know precisely what all the other ones are doing. So that's redundancy. This is often illustrated by using logic gates. So the XOR gate is the one that has most synergy. It's totally synergetic, and pure coupling is over there. The OR gate is somewhat in between, so it's a bit like a symphony orchestra, right? A symphony orchestra that's completely redundant is not very interesting to listen to because that would correspond to all the instruments playing the same. On this kind of stochastic process, by that I mean turn now the XOR gate and the copying and so on into a stochastic process in the following way, that you choose the individuals x1 and x2 at random, and then the third is given by the XOR of those two. Or, of course, in the copying, you choose the first at random, then the next one is a copy of that, and the third is a copy of this. If you make these processes, you can use that to test different measures, information theoretic measures of synergy. And Fernando Rosas and Pedro Mediano some years back came up with this measure, which is called O information or omega information. And I'll just show you, rather than explain all the details, I'll show that it has this ability of being sensitive to redundancy and synergy in the following way. So along this axis, we have the omega. Along that axis, we have another information theoretic measure called sigma that tells you, as you can see immediately, something about how far you are from independent. So what has been done here is that you take these different processes and then you mix them. You can think of it like a slot machine, that the outcome of the slots sometimes comes from a probability where they all three develops independently. Sometimes they come out as a process of copying or as X or, and then you mix these linearly. So you always start out here from totally independent variables, and you see the omega is 0, and so is the sigma variable. Then you mix independent more and more with pure XOR, meaning that a certain fraction of the times the slot machine shows the outcome of purely independent, and the remaining number of events are given by XOR. And you see that as we go towards mixing in more and more XOR, the omega becomes more and more negative. So in that sense, it demonstrates that the measure is sensitive to synergy. And if you do the same and take independent and mix in pure copying, you go the opposite direction and becomes more and more positive. Now, I want to show the use of this, and I'm not sure if this is going to work. First, we have here an analysis of an experiment we have done together with the Guildhall School of Music and Drama, which is a big conservatoire in London. And the experiment is the following, which is interesting. I need some water. So the issue is the following, that in conservatoires in Europe, at least, so Western music, it has become popular to say, I can say, over the last 100 years, not to train the musicians in improvisation. Until then, until 1914, 17, this was part of the education. So of course they would learn how to play classical music, but they would also be expected to be able to improvise on top of that. And there are many anecdotal examples of this. One is that Chopin, when he taught in Paris, would be angry with his students if they came and played the same piano piece exactly the same way twice. And it's also you also see it in the scores from people like Bach at that time, that there were very little information about how to actually play the music, because it was expected that the musicians themselves could find out the best way to do it for that specific performance. And finally, of course, there are the cadenzas in concertos. Anyway, that ability of improvisation has moved out of the syllabus, and there are certain musicians that want it to move back in. And I accidentally started to work with a pianist called David Dolan many years ago, who teaches improvisation. But apparently that's an uphill struggle in Europe, at least, because there are other schools of musicians saying that, this improvisation is just something you do because you didn't bother to prepare. So David wanted hard science to show that it's good to do improvisation. So we did some experiments where we measured the EEG activity of the musicians, and actually, I see that I'm talking about another. Let's drop this one. I thought that had gone. Well, we'll get back to music. Let me just tell you. So this is medical study, obviously, schizophrenia. And we want to see if we could use omega information to characterize the difference between schizophrenic and healthy. And what you see is that the omega is more positive for the schizophrenic than for the healthy, meaning that in synergy, in the sense of this measure, is more, you have more of it in a healthy brain than in a schizophrenic brain. Sorry about this. We go to the one I was actually talking about. So now, after having seen that it can be used for people in medical conditions, we want to see if we could use it on this music study. So what we show here is the behavior of omega for a trio, a flute, piano, and singer that, of course, play music together. And they do it in these two different modes. The one where they use a degree of improvisation in order to make the music lively and interesting and so on, and that we call let go. And then they also play the same music in a strict mode that they say would be the one they use at a competition for classical musicians. And you see that when we plot the amount of omega or the difference in the amount of omega in let go versus strict, that the let go version is more synergetic. And this is in itself an interesting and long talk. There are many, many measures that show that the audience is more happy. They're more engaged. The audience and the performers are more interconnected when they do let go versus strict. But I just wanted this as an example of a data set where you can use the omega information to try to get some feeling for what might be the difference between the two situations. Now, this is the tricky part, because I wanted to play music now in order to show the difference. This is a piece of work done by, it's from this paper, but it was Fernando Rosas who actually did this specific analysis. So he did it on the score of a piece by Bach and a piece by Corelli, and wanted to see if one could understand the structure of the music in terms of redundancy and synergy. And what you see is that the blue lines, those where there's more synergy between the performers, and the red lines are those where it's dominated by redundancy. Can we try to see if the music will play? And let's try to do the same with Corelli. So now at least you've heard the difference between synergy and redundancy. The musically, all what is happening is that Corelli makes much more use of the music of the different instruments, playing essentially the same, or at least something that's much more similar, where Bach do the exact opposite, that he creates a bigger picture, if you like, by the different voices. Now, finally, what we are after in science is, of course, causal relations, although I think certainly after yesterday's talks by Diemer, we all agree that causal relations is a difficult concept. Nevertheless, it's of course what we're always trying to pursue. And now the question is, to what extent can you identify causation by use of information theory? This was what Granger, a British economist, had in mind when he defined Granger causality back in the 60s, I believe. And we'll use it to see if we can, or we'll use that thinking, not his measure, because his measure is simply fitting to auto-regression models. So we'll use information theoretic measures like transfer entropy. The question is, can you identify a macroscopic variable that somehow summarizes or comes about from all the different individual components such that that macroscopic quantity has some causal autonomy, that it predicts in the sense of information theory itself better than, it can do that without knowing the individual components. And for this measure psi was developed, that simply the mutual information of that macroscopic variable at time t and a later time t prime minus the mutual sum of the mutual information by the different components and the collective variable. And the idea is that if this psi is bigger than 0, then there is some robust emergence. So that would be the way to identify the vortices or the class structure in society, or something like this, right? Or maybe more realistically, structures in how the brain operates, which was attempted here, where so this is electrodes on a archaic monkey, the output from the different 64 channels. This is the position of the, I think, the right wrist of the monkey. And then here is psi between the individual channels and the position of X, position of the wrist. And the idea is that psi is positive, so it has some degree of autonomous stochastic behavior. So confirming that the position of the wrist is controlled by the monkey's brain. This is very encouraging, but we need to keep in mind that it is only statistical. What I'm now going to say is not more surprising than the fact that you can, of course, have a high correlation between two quantities, and nevertheless they are independent. The Pearson correlation coefficient can be positive, right, for independent quantities. So it would be tempting to hope that this measure that we just introduced would somehow immediately be useful to identify mechanical relations. So we tried to test it out on random walkers, but independent random walkers. So they just jump along right and left, completely independent of each other. And the center of mass, of course, you can compute, but it doesn't really mean anything. If you have the center of mass of a cloud, doesn't really tell you anything about the macroscopic identity of the cloud. There's just a point in space, but it doesn't. It's very different from a cannonball, right? The center of mass of the cannonball is a good measure of where the cannonball is. Unfortunately, the psi for this kind of set of independent random walkers can be positive. Okay, that's what we found. And I would have liked at least it to be zero, because you don't want the independent stochastic processes to be considered as emergent causal if they're not interacting. But, well, I said it before with the correlations, but I said it wrong. The point is that you can have zero correlation and strong interaction. What I said was wrong. It's you have zero correlation, but dependent variables. And that's similar to what we had here. We have a measure that turns out to be non-zero, but it's for a set of stochastic variables that are not really depending, or they are not dependent on each other. So that's just to say that despite of this psi measure probably being a good indicator of something that could be related, namely, like, for instance, the position of the wrist of the monkey and its neural activity, it's not indicative necessarily of mechanistic connections. But it shouldn't come too much as a surprise. We just need to keep it in mind. Yes. Okay. So I have tried to persuade you that we should all, no matter how we deal with complexity science, keep the insisting that we have a specific type of science. It's not just interdisciplinary and so on, because otherwise we might run in trouble. We are adding something to interdisciplinary studies, right? Because complexity science itself try to identify these emergent properties that can appear in completely different interacting systems. And, well, I don't need to repeat again. That's what we did. So, finished. Thank you very much.
Thank you very much, Henrik. So we have 2 questions, and then we go to have lunch.
Well, I enjoy very much all your examples, and I congratulate you for this relation, Georgia O'Keeffe-Einstein, that I've never heard before, and I will use it and quote you. I will tell you that it's your idea. And I don't know if I understood correctly. Did you say that in UK, complexity science is not considered like a field of research? Is that correct? Mm.
Just to demonstrate it on, in the simple sense that there used to be a certain track where you ticked a box and said that should be considered by the complexity panel. They closed that panel.
I see.
So now you can send it in and you say, oh, I have this very interesting study and I interact with a neuroscientist and a statistician and this and that. And so it's highly cross-disciplinary, and then it goes into the cross-disciplinary field. But it means the effect is, of course, where would you go with stuff like the information theoretic analysis of how you in a specific situation
like arises from coordinated interactions or simple components, or most genuinely complexity also entails self-organization, understood as the system autonomous capacity to generate and sustain its own patterns. The airplane's behavior depends on an externally imposed design and not on internal dynamics. Does this mean that emergence alone describes a relational effect, while true complexity requires an intrinsic principle of self-organization autonomy?
Oh, yeah. That's, of course, a deep question that's difficult to answer briefly, but I think we could think about what I say as the person from the research council comes and ask you, so what is, why do you call it complexity science? What is this complexity science about? And then I'd say the minimal definition is the one I've given, that there should be emergent properties. And the airplane is, of course, a good example. There'll be a lot of what happens around an airplane that is fully expected. And then sometimes they're disasters, right? Just think, isn't it the Boeing Dreamliner that went down twice because their anti-stalling system did things they hadn't expected? And that's, of course, in a very dramatic and dangerous way, an emergent property you hadn't anticipated. Whereas when the airplane flies happily along and brakes and all that's precisely what the engineers have designed it to. And I agree, of course, that maybe it's more interesting with emergence in self-organizing systems. But that's sort of degrees of emergence. That's it.
Yes, now we can go to have lunch, same place every day. Thank you very much. Aplausos, muchas gracias.